Hey everyone, so today we are going to be looking at recurrent neural networks for generation. So in the last video we took a look at classification of a sequence. Now we're going to be looking at the generation of a sequence. And this should start making you think about this many-to-many model, where we have some inputs and we want to generate some outputs. Right, so let's go ahead, and there'll be a little bit less theory in this one, just a couple of drawings to outline what we want to do. But let's go ahead and just kind of dig right into it today. So we're going to import torch torch.optim as optim, import numpy as np, and import os. That's, I think, all we need. So before we get into the generative portion, I do want to talk about one other thing about the LSTM. So if you remember, last time when we looked at LSTMs, we took a look at this really amazing figure where we see that we pass in a sequence of inputs, and the model, the LSTM module from PyTorch, will output a sequence of hidden states. We also get the HN and CN, the final hidden and cell state, but we typically don't care about this as much right now. So what we're doing here is we're passing a sequence of inputs, and it produces a sequence of outputs. So that's all well and good, except that we have a little bit less control here. So in the last video, we just passed the sequence in and we were done. And what I want to show you today is there's actually two ways of doing this. We can either pass the sequence in, and PyTorch will again for loop through the sequence, because the recurrent neural network is a for loop through the time steps. So we can either do that, or we can do the for loop ourselves, right? So we can manually do the for loop. So let's just do that real quick. I'm going to copy this chunk in. There we go. So I'm just setting ahead of time the batch size, sequence length, the input size, so the embedding dimension of the input, the hidden size, the projection that's inside, and the number of layers. If these words don't make any sense, you probably need to look at the previous video. I'm not going to be talking too much about the LSTM or the RNN or anything too much today. I just want to show how to use it and then what the generative or the autoregressive task actually is. So again, look at the last video if you're confused on kind of the introduction to recurrent neural networks. So let's go ahead and define our LSTM. So it'll be nn.lstm, LSTM, and it's going to be input size equals input size. The hidden size is the hidden size. There we go. The number of layers is the num layers, and batch first equals true. So there's our LSTM model, nothing too crazy. And we're going to pass data into this in both ways. So let's first generate some random data. So we're going to do rand is equal to torch.rand. And we're going to, in the typical shape of sequence problems, we have some batch size by the sequence length by the input size, or the embedding dim. There we go. So we have our random data. And so let's do method 1. So method 1 of passing in our data. So this is what we did last time. We just pass our sequence into our model and we're done. So we can do method 1 out is equal to, and actually HN and CN, we get both the hidden and cell state of the nth time step as well. It's going to be the LSTM model where we pass in rand, and that's it. So method 1 out.shape, and there we go. We passed in a 5 by 15 by 10, and it outputs a 5 by 15 by 20. Again, we talked about what these shapes and everything are last time, but as a recap, we have a batch size of 5. Each sample, each sequence, we have 5 sequences. Each sequence is of length 15, and each time step in the sequence is represented by a vector of length 20, and that's it. It also returns our hidden state and the cell state, so we can look at those as well. nhn.shape. And cn.shape will be the same thing as well. So this is our hidden and cell state. So this is the number of layers by the batch size. We have 5 samples, and by 20. So there we go. The hidden size. So this is fine. There is one thing we skipped. So technically, we can also pass in the initialization, H0 and C0. H0 and C0 are just initialized as, well, zeros when we start out. So we're going to do H0 is torch equals torch dot zeros, and in torch dot zeros we're going to, the shape that they expect is num layers by batch size by hidden size. And then C0 will be exactly the same thing. So C0 is exactly the same thing. And there we go. We have now initialized the hidden and cell state, though if we don't initialize the hidden and cell state, PyTorch doesn't really care. It will initialize it for you. But there we go. We now have our method 1 of doing it, and this should look familiar because this is exactly what we did last time. Method 2 is where instead of PyTorch for looping through our sequence length, why don't we do it, right? We will for loop through the sequence length. So again, we're going to do a, I'm going to call this, we're just going to copy this because we're going to need you again. But now instead of H0 and C0, I'm just going to call them H and C just for convenience, and you'll see why. So we have H and C, and we're going to create a empty list called outs, where we're going to store the outputs, and we're going to do for I in range sequence length. We're going to do, we're going to do a token is equal to rand I. So what we've done here is, and this as well. So what we're doing is we're looping through the sequence length. So we're looping in this tensor here, this rand tensor, we're looping through this dimension here. So what we're indexing is we want this dimension, the ith time step in this dimension, but we want for all the batches, so all the samples in our batch, and for the entire hidden, the input size, right? So we can look here, print token.shape break. I should have done sequence length here. And notice it's a 5 by 10, which makes sense. This is a 5 by 15 by 10, and we just grabbed one of those 15, leaving us with a 5 by 10. So there's no problem there, except the LSTM module won't be happy with this. It actually needs that dimension in here. So we're going to make this a 5 by 1 by 10, right? So 5 by 1 by 10. So we're going to add a dummy dimension in there. There's a bunch of ways of doing this. The easiest one is unsqueeze. Unsqueeze. If we do unsqueeze 0, it will produce a 1 by 5 by 10. So notice it put the 1 at the beginning because we said we wanted on the 0th dimension. If we do unsqueeze 1, then it's 5 by 1 by 10. It places it where we want it to be. So there we go. We have our token being ready to go. So that's one of our 15 tokens, all the samples in the batch, and the entire input size for that token. So there we go. Next, we can do out, and then hidden and cell is equal to LSTM token hidden cell. And this is the most crucial part of this implementation. So what we see is we're passing in some hidden and cell state. That's right here, along with the token at this specific time. And it returns a new hidden and cell state. And because H and C are the same variables, the new hidden and cell state will replace H and C. So that this will become so H and C went from the original zeros to something new. And we get a single output. So if we print output.shape, or just out.shape, sorry. Out.shape, we get a 5 by 1 by 20. This makes sense because we had batch size of 5. We only had one time step that we passed in, and we had an input size of 10, but a hidden size of 20. So 5 by 1 by 20 makes total sense. We also have our H and C. So the shape will stay the same, but we can look at H. Notice how H now is not all zeros. Something has changed. And this was initialized zeros, and now they're not zeros because we've actually updated the hidden state in this step. And as we loop through our time steps, the old hidden state is passed in, and it creates a new one. And same for the cell state. And we just rinse and repeat over and over again until we've exhausted the entire sequence. So again, the updated hidden state and cell state represent the history of the sequence, right? What happened in the past. And as we pass in the hidden and cell state and pass in a new token, it updates the hidden state to include the new token in this history. And going back to the figure, all we've done here is instead of just passing in a sequence of X's and producing a sequence of H's, what we're doing now is we pass in a single X, and it produces a single, and ignore the number of layers for now. So just ignore everything in the middle. We pass in a single X, we produce a single H1W. right? That's right here, H1W. But notice H1W goes up into the output, but H1W and C1W, the cell state as well, goes to the right. So this means that we passed in an X1 along with a initialized H0, C0, and it produces an H1, which is our out. But in the next step, when we pass in X2 for the next step, we just push the existing H1 and C1 as well. So X2 and H1, C1 become the new input to this thing to then produce H2. And we rinse and repeat over and over again. So that's exactly what it's doing. We're passing in one time step at a time, and we're updating the hidden and cell state over and over again for each of those time steps across the batch. And we also produce an output, and the output is just H1, H2, ... up to Hn. So we can go ahead now and store in our outs .append out. Right, we're going to just go ahead and store that. And our last step to do is what we have right now is a list of tensors. That's obviously not helpful for us. We just want a tensor. So if we do method toOuts is going to be torch.concat outs. And remember each of these outs. So if we do print outs 0 dot shape, this output is a 5 by 1 by 20. So we're going to have a 5. Each of these outputs are all 5 by 1 by 20. We just want to concatenate it together on this dimension. So if we had 3 5 by 1 by 20s, then it should become a 5 by 3 by 20. So we want to concatenate on this dimension, the first dimension. So let's go ahead and do that. We're going to concatenate outs, but we're going to do our axis equals 1. And so now we have our method toOuts. And the verification now is all close. We have method 1outs and method 2outs. Are these the same? And they are. So all close is because there might be some like little floating point precision errors that makes them slightly different from each other. But overall, they're very close together. I think like 10 to the minus 6 or something is what all close uses. So they're very close together, and we are now good to go. So again, these are two methods of doing the exact same thing. In one of them, we just give PyTorch the sequence and it does the for loop for us. In the second one, we manually do the for loop. And we will need to be able to do this when we actually do sequence generation. And you'll see that a little bit later. So let's talk about how we build a data set for next token prediction and what next token prediction is. So what we want to do is open this. And I want to talk just a little bit about what it means to do autoregressive generation. So it's called autoregressive regressive generation. Right? So what is autoregressive generation? Let's pretend we have three inputs. We're going to say x1, x2, and x3. Right? So this is my input sequence at 3 time steps. And my question is, right, if I want to predict the future, the next time step, I have to predict x4, right? What is x4 is my question. So there's all sorts of models we can use. Today we'll be using the recurrent neural network, but you could use you could do a causal convolution. You can use transformers, or you can use Markov models. You can use all sorts of stuff to do this, but we need something that can model this sequence. So x1, x2, x3, and it needs to predict x4. What would x4 be? And so let's say we do that. So this is step 1. Let's say we complete it. Let's say we predict something for x4. So now step 2 is we have x1, x2, x3, our original input, but we've also predicted, let's include that, x4, right? We have some, we don't know if it's right or wrong, but we do have some prediction for x4. Now that we have x4, we have a new question. What is x5, right? The next time step. So now we are using x1 through x4 to predict x5. And the reason this is called autoregressive generation is notice that a prediction from a previous step, right? We predicted x4 becomes an input to the model for a future step. And that's why it's called autoregressive generation. And so this is effectively how most things like our large language models today. So if we look at like GPT or Llama, or really any of these large language models. Or if we're doing stock price prediction, we need to predict, what the price will be tomorrow, the day after, a month from now, all sorts of stuff. These are all types of autoregressive generation. And it's autoregressive because a previous output becomes a future input to the model. So there we go. That gives us a general idea for what autoregressive is. So what we need to do is build a data set for next token prediction, which is just another way of calling it autoregressive. Let's take a look at how we can do this. So today we'll be doing a character level model. Character level models are not recommended, and we'll talk a little bit more later about why. But we're doing this today just for the purposes of simplicity, to make this as easy to understand as possible. So let's try to talk about autoregressive generation for the purposes of text. So let's do a quick sentence. Let's do, let's say the capital of France is Paris. And for now, let's pretend we're doing a word level tokenization. So every word is a unique token. So, we'll grab, let's say this is word 10, and let's say this is word 6, and word 9, word 11, word 22. I'm obviously just making up numbers here. And word, I don't know what number they know. Let's do 4, right? Whatever. And so we have a tokenizer, right? Tokenizer. And there's going to be some n unique tokens in it, right? And these are some of those tokens. These are 6 of those tokens. So we have these things. And what we need to model, and we'll kind of explain how we do it functionally, and then how we do it with the LSTM. What we need to model is this sequence. And so the question now becomes, given the word the, right? Let's just start at the very beginning of the sentence. Given the word the, we want to predict the next word, and it's always the next word, capital. And then given the word the and capital, we want to predict of. And then given the capital of, we want to predict France, ... So do you see what we're doing here? We're basically asking, given the history, the previous words, what is the next word, right? So if we want to predict Paris, we want to predict Paris given the capital of France is, and then we want to predict Paris. And this is the big idea, right? This is the main idea that we try to explore with autoregressive generation. And so let's talk about how we do this with an LSTM. But in all practical cases, most architectures of this sort of stuff today is implemented with transformers, but transformers is just another type of sequence modeling, which we'll explore a lot in the future. This is just to set the stage. So let's go ahead and think about it in terms of our LSTM. So LSTMs have inputs. We'll have the is the first input, capital of France is. And we're going to stop right there, and you'll see why in a bit. So these are our inputs, right? x0, x1, x2, x3, x4, right? These are our input time steps, and pretend we've tokenized them and embedded them and all that sort of stuff, so that's fine. And each of these are going to produce some hidden state, right? So we're going to have a h0, we're going to have a h1, we're going to have a h2, hidden 3, and finally hidden 4. Those are my outputs. But again, because this is a recurrent neural network, we also have this pathway right here, right? And now given the, like we saw before, given the, we want to predict capital. So we're hoping this hidden state, and we'll see functionally how we implement this in a bit, but this hopefully will predict capital. And then given the and capital, we want to predict of. So we're hoping this thing can predict of. And then given the capital of, we hope we can predict France. And then the capital of France is, and then is, and that's our Paris. So let's see why this works. We want to predict the predicts capital. No problem there. That's our pathway. We also the next thing we predict is capital will predict of in this way. But it's not just capital. Remember, this hidden state here, H1, represents not only the input, the current input, the current time step, but it also represents the history of time steps. So we also have information from H0 coming in, and H0 was made by X0. So to predict of, we're really being informed by X1 and X0 through our H1 hidden state, which has accumulated that information. If we keep going, right, if we keep moving forward, when we want to predict Paris, Paris is predicted by is, but it's also informed by France, it's informed by of, it's informed by capital, and it's informed by the. So the capital of France is, the entire history, the capital of France is encoded into H4, which then predicts France, or sorry, then predicts Paris as our capital. I hope that kind of intuitively makes sense. This should feel familiar because we talked a lot about this in the previous video about kind of how these recurrent neural networks process stuff in the history. But let's kind of mention one problem here. And this is the problem we've already talked about before, sequence length or context length, right? Context length. Unlike transformers, which we'll again explore later, recurrent neural networks don't have huge context lengths. It's not like I can just ask the LSTM to write a book, right? You can't just generate a whole book. Because let's pretend we have x1, x2, ... x 10,000, right? 10,000 words seems like a reasonable amount of words in a book. Will x1 and x2 be able to form x 10,000 through hidden 10,000? Probably not, right? This information, due to the backpropagation through time and due to gradient underflows and vanishing gradients and things we've talked about in the previous video, this won't happen. So this is why LSTMs aren't really used for large generative tasks, for text especially. But again, this is just to set the stage. But this should make sense. The main thing you should take away, though, is how we prepare the data. So our original sentence was the capital of France is Paris. Notice the input to the model. The input sequence is the capital of France is, and the output is capital of France is Paris. So what we end up doing here is we take all this, and our input will be the capital of France is, and the output will be capital of France is Paris. Because we want to predict from we want to predict capital. So remember, we have to pair them up. The tensors have to align, right? So the will predict capital. Capital will predict of will predict France. France will predict is will predict Paris. But because of the LSTM module, we'll also have these interconnections between them, right? And through the hidden states. So we just need to align them and set it up that way. So the way we're going to do this today is a simple character level model on a very simple Harry Potter data set. So we have a little bit of work ahead of us just to clean up and prep that data. But once it's ready to go, it's ready to go. The reason we're doing character level modeling again today is just for simplicity. But obviously a better model would be a subword or a word level model. The reason this is the case is because if you imagine the vectors, the embeddings that we learn for each token have to represent the quote unquote meaning of the word, or at least how what it means in context or reference to the words around it, right? The other words in our data set. Words have meaning that makes sense. So there's something you can learn there. Subwords also have meaning, right? Like if you have words like I am the happiest person in the world, happiest could be split into happy and est. Happy has meaning and est has some meaning in the case of how the English language structure works. So those things still have meaning. If we do a character level model where we turn the word apple into A-P-P-L-E, there's two problems with this. Number one is each letter doesn't really have meaning, so it's kind of hard to say like what P means. It's not a thing. So when we're training it, the embeddings are less interpretable is probably the best way to say it. The second thing is sequence length. So like I mentioned, RNNs and LSTMs, regardless of how powerful they are, they still don't have long context capabilities like transformers do. And splitting a single word into 5 letters. So this will now become 5 tokens in our sequence. Splitting a single word into a sequence of tokens will greatly expand the sequence length of our problem. And that's, a problem, obviously. We don't want to do that. We'll end up dealing with long sequences. In the real world, we would never do this, but we're doing this for simplicity today, just so we can kind of work with what we have. So we're going to do path to data is equal to, so I think I have it stored in here. Again, we're doing the Harry Potter text, which is in my GitHub, so you can see it. You can see where I got it. And it's basically just a bunch of text files. We're going to do text files is equal to os.listdir path to data. So let's look at text files real quick. And as you can see, it's just the books, right? The 7 books in Harry Potter. So nothing crazy. So what we're going to do today is just grab all of the text, store it in one big text file or one big string. And there's just a little bit of cleanup that needs to be done. And you'll see that in just a bit. So we're going to first do for book in text files. For every book. We're going to go ahead and do the path to book is going to be os.path.join between the path to data and the book itself. So we just have that full path. So a break in there so we don't iterate through everything. And we can do with open path to book in reading mode as f. Text is f.readLines. And we can print, let's just print out the first 100 items, first 100 lines in text. And there's a couple things you're going to notice that's a little annoying. First of all, we have all these random new line characters that we want to get rid of. So we have a little bit of work to do there. And we also have these things here. So at the end of every page, we have like a page 2, then we have a page 3, and I'm sure there's more, right? So we have to get rid of these as well. So let's just go ahead and do a very basic cleanup. So first of all, let's get rid of the pages. We're going to do text is equal to, we're going to loop through all the lines. We're going to do line for line in text if page not in line. Obviously there might be other lines that aren't these pages, like these page number lines that are in there, but again, for simplicity, I'm just getting rid of them. Obviously there's better ways to do this stuff. Next, we want to get rid of the new line characters. So we're going to stick together all of our text. So we're going to do text is equal to dot join. So this will take all of our text. Let's print out the first 100 again. Text. Line for line in text if page not in line. There we go. So here's our text. Notice there's all these new line characters and stuff that we just want to clean up. So what we're going to do is dot replace new line character, which is \n, with an empty character. And that gets rid of some of those new lines. But we still have some blank characters and other stuff to deal with. So let's go ahead and do that. We're going to split our text into words now. So we're going to do word for word in text dot split. Again, we're going to split on spaces, assuming there's space between every word. So if we do this actually, so before I keep going, oh, I shouldn't have printed it all out, but that's fine. Let's go to the top. Notice we have some words in here that are just blank tokens. So these are the empty tokens coming up from those new lines and stuff like that. So let's go ahead and remove them. We're going to do text for which is word for word in our text if len word greater than 1. So there has to be at least one character in our word for us to keep it. Oh, and then we can print text, and let's just keep the first 100 things. And so that cleans it up quite nicely, right? We've removed a lot of that kind of filler text, I guess. Now that we have that, we can do text is finally dot join text, put it all back together, and we can do all text plus equals text, just like that. And so let's go let that run. Oh, I didn't create it. All text is just an empty string, and we're going to just go ahead and store all of our text, and now we have all text. If we go ahead and do len all text, we'll see we have about 6.1 million characters. 6.2 million characters. Is this 1, 2, 3, 1, 2? Yeah, 6.2 million characters to play with, right? So that's quite a number of characters to train on. So that seems pretty good. What we want now is a character level tokenizer. So in the previous video, we did a word level tokenizer where we found all the unique words in our data set. Now we're doing a character level tokenizer. So we just need to find all the unique characters in our data set. And that's pretty easy. We can do set all text. This is the list of all the unique tokens, characters in our data set. We have some weird ones, but I'm not going to bother cleaning anything right now. Just keep it as simple as possible. So set, I don't like it as a set. We're going to convert it to a list, and we're also going to go ahead and sort it just so it's nice and ready. So we have now a list of unique cars. Unique cars. Right? So there's all of our unique characters. And now we need to assign a unique number to each of these characters. So there's, I believe there's 91, or no, looks like there's 88. So there's 88 characters here. And so yeah, what we need is just go ahead and keep all the unique characters. Actually, one small mistake. If I do len word greater than 1, that'll get rid of one letter of word. So we need to actually do len word greater than 0. So any empty characters is removed. So now we should have 91 characters. There we go. That's what I expected. There we go. So we have our unique characters. Let's go ahead and create our tokenizer. So car to index is going to be ci for index character in enumerate unique cars. And then index to car, going back the other way, it's going to be ic for ic in enumerate unique cars. And there we go. So in the previous video, we only needed the ability to convert the characters to their indexes so we could tokenize them, pass it to our embeddings, that sort of stuff. So that was fine then. Because we're generating now, we actually need to go back from those indexes to the characters. So we have a little bit of work there, but we'll get there when we get there. So that's fine. So we now have our character to index. We can actually take a quick look at this. We basically have all of the unique characters. Notice there's uppercase and lowercase letters, and each letter or character or space or symbol or whatever is given a unique number that goes with them. And we'll need this for our tokenizer. Oh. There we go. So now we need to build a data generator, and this should be pretty straightforward because we already talked about how we sample the data. So let's go ahead and do this. So data build. Actually, let's talk about one thing before we do this. There's a slight difference between how we do data for this task versus what we did in the last video. So in the last video, notice we don't have any padding tokens or anything like that in this specific implementation. The reason for this is in the previous video, when we were working on kind of we have some sentence, and then they go with a classification or some label, right? And then we had another sentence, and then another label, and then ... We had a bunch of these. We needed to stack sentences together to actually predict the label. But the problem is different sentences are of different lengths. So we can't really stack sentences together if they're of different sizes. So we need to pad the shorter sentences to the longer one. And this is why we spent that time writing that data collation function using the utils.rnn, the pad sequence function. In this case, what we have is a big block of text, right? We have text with about 6.1, 6.2 million tokens. I can then decide I want to work with sequences of some length. I'm going to do 300 today, but it doesn't really matter. You're going to pick some sequence length. And then all we need to do is just grab random chunks of 300 consecutive tokens from our data. So if we do it this way, every chunk, if they're all the same length, then I have no problems. If all the chunks are of exactly the same length, then I can just go ahead and stack them together without needing any pad tokens or anything like that. So it's a slight difference between how we did it previously versus how we did it now. So let's go ahead and write it. So class data builder, and this is how data is typically prepped for this autoregressive task. We just grab random chunks of some sequence length that we decide ahead of time, and then we just train our model with that. So there's no padding necessary. But when we do things like the classification, then we can't just grab random lengths. We have what we have. It's what we are provided by the text. So we can't just grab a random chunk. It doesn't really make sense there. So slightly different, but it is what it is. It's not that we couldn't have pad tokens here. It's just we don't really need them for at least a simple implementation. So we're going to sequence length is sequence length. Right, so we're going to store that. Self.text is text. Self.file length is equal to len text. So this will tell me how many tokens do I have. This is the text itself, and this is how many tokens do I want to sample every time. So we're going to write two functions, grab random sample self, and then we're going to have a def grab random batch self batch size. So obviously we need to write the logic to grab one sample at a time, and then we will be grabbing batches of them at a time. We could have also written an actual data loader for this, but we don't really need to. This is simpler, so we're going to keep it as simple as possible. So yeah, we first write the logic to grab one sample at a time, but we train on batches. So in the future, a little bit later, we'll have to kind of call this sample over and over again to just grab random batches. So let's go ahead and do this. So we need to pick start. So the way I like to do this, there's obviously a bunch of ways of doing this. Let's say we have word 1, word 2, word 3, word 4, word 5, word 6, word 7, word 8, word 9, word 10. So we have, let's pretend this is our entire data set. We have like 6.1 million tokens. Let's pretend we only have 10 tokens. And we decide some sequence length, right? This is up to us. Let's just say we pick 3. That means if I pick 3 consecutive tokens, I can pick 1 through 3, or I can pick 2 through 4, or I can pick 3 through 5, 4 through 6, ... and 8 through 10. What I can't do is pick 9 through, because there's nothing here, right? There's nothing here. So all I need to do is, if I can go up to 8, I will randomly select some starting index between these, and as long as I don't go too far in, then I can go ahead and always have a complete sequence, right? A complete sequence. And so we're pretty good there. And so let's go ahead and do that. So we are going to do start is going to be np.random.randint. And we can pick any random integer, any random starting point between 0 and the self.filelength minus self.sequence length. As long as we're in that as long as we're between there, then we're good to go. So we're going to generate some random number, just like that. And this means when you do end is equal to start plus self.sequence length, we won't spill over the edge of our text, right? So we're within the number of tokens that we actually have, no matter what. If we then do this, then it just leads to like a bug, right? You'll basically, you could potentially, when randomly sampling, have a sequence grabbed that's shorter than the sequence that we have, which would be then the sequence length that we want. So we wouldn't be able to stack the tensors together, and then we'd have the whole padding issue again. So this is to keep it as simple as possible. Now that we have this, we can go ahead now and grab the text slice, right? So text slice is going to be self.text from start to end. So there we go. And now we can do input text is equal to text slice everything except the end. Okay, so this goes back to this idea again right here. This is our sentence. Let's say our slice had 6 words in it. The capital of France is Paris. That means the input is the capital of France is, so the capital of France is, and the output is the is just capital of France is Paris. So the input is everything but the last word, and the output is everything but the first word. And we're doing exactly that. So the input is everything but the last word, so we index it out. And then our labels, the targets that we want to do, is going to be text, the same text slice. It's going to be everything but the first word. And then the last thing we need to do, these are still characters, right? They're going to be letters in our data. We need to actually tokenize them. So we can do input text is going to be car to index C for C in input text. And then our label is going to be car to index C for C in label. Right? We're going to loop through our each character in the input text, each character in the label, and then access its corresponding integer value that represents it in our dictionary. And obviously, we don't want them as lists. We want them as tensors. So we can do torch.tensor. And there we go. Torch.tensor. And we can now go ahead and return. We can go ahead and return input text and label. And this is just me grabbing one sample, right? Just one sample. But we obviously have to train on batches of samples. So let's go ahead and do that. So we can do input texts, plural, and labels. We're going to make them 2 empty lists to store stuff in. And we can do for blank in range, whatever batch size we pick. We can grab a sample. So input text and label is equal to self.grab random sample, and that's it, right? We're going to grab a random sample, which will be some random input text and its corresponding label, its offset label. And so now we can store input texts dot append input text, and then labels dot append label. And to finally wrap this up, we can do input text is equal to torch dot. We have a list of things, right? So we just need to stack them together. So input texts, and then labels equals torch dot stack labels. And then we can return input text labels. We could have also used torch dot concatenate or cat. Cat and stack are actually slightly different from each other, so I can show that right now. So let's say we have A is torch.rand and 5, and B is torch.rand and 5. If we do torch.stack A, B as a list, has to be a list of tensors, it will automatically add, so dot shape, it will automatically add that extra batch dimension 2, right? So it just stacks them together. On the other hand, if we do torch.cat, it'll actually just put them together as like one long vector of 10. So if you wanted to do the same thing as stack, we'd have to first do unsqueeze 0 here, dot unsqueeze 0 here, and then we'd have to mention here that dim equals 0, which will give you the same result as what stack had just done, so it's just a shorthand. So stack will automatically unsqueeze on the first dimension and then concatenate on that dimension, which is exactly what you want. So there we go. So now we can quickly test this out to make sure this works. So we're going to do dataset is data builder. And I'm going to do a sequence length of 10 for now, just to make it easy to see. And we can do input texts, and labels is going to be dataset.grab random batch. We're going to grab a random batch with a batch size of, let's say, just 4 for now. And you should see your input text right here, right? So we have 4 sequences, each have 10 tokens in them. And there we go. Let's print out 0 for each one and its corresponding labels, just so we can see what that looks like. And we have to print both of them. Okay, there we go. So notice the input 69, so it goes 69, 77, 68, 0, yada, yada, yada. And notice how this sequence is just offset from this one. So 69 becomes, we want to predict with 69, we want to predict 77. Using 77, we predict 68, which is the next thing in the sequence. Using 68, we want to predict 0, which is the next thing in the sequence. So this sequence and this sequence are just offset from each other, just like we saw before. So we have our inputs, labels, and we're ready to go. Now it's time to define our model, right? So this is the interesting part. And there's two things we need to do to actually define this model. First, we need the regular model stuff and the forward function, and that's all fine. It'll look very familiar to what we had done before. On the other hand, we also need to write the generating function, like the thing that will actually write text. And how the write function will work is we're going to provide it some text, and it just has to continue writing more from there. And so we'll kind of go with that. So let's do class LSTM for generation, and then .module, def init, self, and we just need to provide it the usual stuff. So embedding dim is 128. The num characters, so how many characters are in our embedding matrix, will be len, however many, there's 91, but car2 index, so there we go. The hidden size is going to be, I think, 256. N layers, let's just say there's 3, and let's say device is, for now, CPU, right? So there we go. And super.init, just like always. Now that we have all of this, we just go ahead and store everything. Self.embedding dim is embedding dim. Self.num characters is num characters. Self.hidden size is hidden size. Self.n layers is n layers. And then self.device equals device. So there we go. So there's our kind of setup. And now we go ahead and actually write our model out. So this model, the beginning of the initial part, will look very familiar. So we're going to do self.embedding dim, or no, sorry, self.embedding is going to be nn.embedding. And there's going to be num characters, number of tokens, like unique tokens in our embedding matrix, and each token will be represented by a vector of length embedding dim. So there we go. We then need our LSTM. So self.lstm is nn.lstm, and it's going to be input size equals will be embedding dim. The hidden size is going to be hidden size. Our num layers is going to be n layers. And then batch first equals true. So there we go. And then the final thing is how we set up the autoregressive task. And this is, again, a very important aspect of this autoregressive task, what we do to do next token prediction. And this is for what we're doing now, but even for things like GPT and other architectures like these big large language models, they are still classification models. And let's kind of explain what that is. So we pretended, right? Let's say there's n, in our case, there's 91, right? There's 91 unique tokens. And so what we have is, let's draw it out. So we have character 1, character 2, character 3, character 4, right? And then we produce some hidden states here. I'll be a little less detailed about it. So we have some hidden states that go like this. These are our inputs. And we produce outputs, right? And these outputs are vectors, right? There will be vectors that represent, the output is the hidden state. Like it's the vector that represents this thing. So this is a vector, hidden 1. This is a vector, hidden 2. This is a vector, hidden 3. Another vector, hidden 4. Right? And these will all be of, each of these things will be 1 by, I'm ignoring the batch dimension right now. So this is one vector that'll be 1 by hidden size. So this is whatever. So if our input size was 128, like it is in our model, and our hidden size is 256, each of these vectors will be a 1 by 256. Now what we need to do is predict the tokens, right? So we want this to predict C2. We want this to predict C3, want this to predict C4, and we want this to predict C5, right? We want to predict so C1 should predict C2, C1 and C2 should predict C3, dot, dot, dot. We already drew this earlier. The thing is that C2 is not the only option. We have 91 possibilities. So what we can do then, let's just take this first one, right? We have a vector of length. It's 1. It's 256 by 1. And actually, in practice, it'll be a row vector. So there we go. 1 by 256. And we can pass this in an NN.linear layer that takes 256 inputs, and outputs 91. And this should look very familiar. I mean, this is exactly what we've done in every case. But again, if you don't remember, in our MNIST problem, right, we have an image. Let's say the number 2. This is a 28 by 28 vector. We flatten it into a single vector of 1 by 784. And we pass it to an NN.linear that takes 784 inputs and outputs 10, because there's 10 possibilities, right? The digits 0 through 9 are your possibilities, so you have 10 possible outputs. In the same way, we have 91 possible outputs, 91 possible characters the next token could be. We're hoping it predicts the correct one, right? C2 or whatever it should be. But regardless, there's 91 possibilities. And that's the important part to keep in mind. Now, when we actually do this gets a little bit more complicated. So let's just kind of figure it out right now before we go. Our sequence data, right, X, is actually, before we go into that, let's just start at the beginning. So whenever we've been working with linear layers up till now, we can do batch. We have a batch by some input dimension. It goes to a linear layer that takes some input and produces some output, and it produces a batch by output dimension. So you can see it's really this last dimension that's getting affected. The reason this is also important is this batch dimension is parallelized. So this operation, this matrix multiplication, is happening for every sample in our batch independently. So one sample in the batch doesn't see the other ones. It doesn't matter if the other ones are there. And that's important, right? The batch dimension has to be parallelized. Now, in the same way, right, what are we doing now? So actually, let's leave it there. Our X now is going to be batch by sequence length by embedding dim, right? That's our thing. So we have batch. So we have, these are how many sequences we have. Each sequence is of this length, and each sample, each token, each time step in this sequence is of length embedding. Actually, instead of E, let's make this I, right, for input. But you get the idea, just to make it the same. But we have a BSI is our shape. Now, this projection, what we want to do is for every sample in our batch and for every time step in our sequence, we want to do an independent projection. Like each of these things should happen independently. So what we can do actually is reshape this. We can make this B, instead of a B by S by I, we can do a B times S by I. So we'll flatten it out, because every projection, this linear layer is going to do them independently. And what I mean by that is when I do this linear layer right here, when I do this linear layer to predict from C2 to the 91, again, there's, if we erase here, there's 91 possibilities here. But we have the same 91 possibilities in each of these steps, right? All of them have 91 possibilities. And so the only time we're doing sequence modeling is here, the recurrent neural network. The linear layer is just a projection. So each of these time steps, each of these hidden states that we generated should be projected independently. independently. In this case, we have a batch size of 1 by 4 time steps here by some hidden size, right? Whatever it may be. So it doesn't matter in this case because 4 times 1, this is just same as writing 4 by hidden because we only have 4 tokens here. But here, if we have batch size by sequence, let's say the sequence is again 4, but let's say we had 10 sentences. That means we have 40 tokens, 40 time steps in total across all the batch and all the time. So it's b times s by I. We can then pass this to a linear layer that takes input, output, and that'll produce a b times s by O. And then we can just go ahead and reshape it again to b by s by O. So we have this reshape operation. This obviously will work. This will be fine. But in PyTorch, actually, we don't need to do all of this effort. So if we take a quick look at the, let's say, nn.linear, here we go. Notice that in the linear layer, it actually has a star h in, star h out. So it actually doesn't care about what all, I mean, we've been just assuming it's batch by h and batch by h, but it can actually be anything. It doesn't matter. So we can avoid doing those reshapes and instead just directly pass in a b by s by I into our linear, where this b by s is the star, right? Like it can be anything. We need to pass this into a linear input, output, and then this will produce a b by s by O, right? Where this is our star. So the linear layer in practice, and we're going to be using this fact a lot in more advanced implementations, the linear layer really just affects the last dimension. Everything else stays the same. Internally, it's doing that flatten and then the linear layer, and then it'll just, put it back how it found it. Internally, it's doing something like that. But for our implementation, for our case, the linear layer just affects the last dimension, right? So it goes from, so you go from b by s by I, pass it from an I to O, so b by s by O. And that's it. That's the big idea. So we can go ahead and implement everything we just talked about. So let's go here, go here. So our self.fc is nn.linear, self.hidden size is what's going to go in, or I don't need to do self, I can just do hidden size is what goes in, and num characters is what comes out, right? The number of possibilities each of those hidden states can take. And we'll see how that works out in just a second. So we're going to do model is equal to LSTM for generation, leave everything the same. Let's do rand is torch.randint. So we need to generate some random integers between 0 and 91. So let's just do 0 and 91. And let's just generate a, I don't know, batch size of 4. And each sample, each sequence in the batch is of length 10. So we have this kind of randomly generated data. We can now do model rand, and we have to write our forward function. So we can do def forward self x. First thing, just like before, we need to embed our data. So x is self dot embeddings x. Actually, embedding singular. So there we go. Print x dot shape. And we should see our 4 by 10 became a 4 by 10 by 128, which makes sense because our embedding dim on the embedding matrix is 128. So we have that. Next up, we can do our pass these embeddings through our model. So output, and then hidden and self state, which we don't really care about, but we'll get them, is self.lstm. And it's going to provide a, we have to provide the x, the embeddings, and a initial hidden and self state, but again, we don't really care about the initial either, and PyTorch will automatically initialize them as zeros if we don't provide anything, so that's good for us. So all we really care about is this output.shape. So we get a 4 by 10 by 256. And again, there's two ways we can pass this through. So what we have here is 4 sequences. Each sequence has 10 time steps, and each time step is encoded by a vector of length 256. So that means I have 40 time steps in total across all the batches. Not 40, 40 in time, but we have 40 total tokens. That's the best way to think about it. We have 40 total tokens. Each token is represented by a vector of 256. And what we want to do is project them to the 91 possibilities, right? Each of these things will have a prediction. Again, going back to our figure, each of our inputs, if we have 4 inputs here, this is a batch size of 1, we have 4 inputs, each of these inputs, we want to predict an output independently of each other. Again, the important part, and we're going to see this when we do transformers in the future, there's always 2 steps. There are the recurrence or the attention or whatever we end up using for our sequence modeling is where the sequence modeling happens. But the linear layer is just a simple projection of that. And we'll again compute loss, right? We're going to compute the error on each of these time steps, right? Error, right? We're going to have some cross-entropy loss, and then that loss will backpropagate back through the model just like this, right? That's effectively what's going to end up happening. So let's go ahead, and we just need to apply this independently. And like I mentioned, there's 2 ways of doing it. I could take my output, I could flatten the 4x10, making it a 40 by 256, pass it through my linear layer, making it a 40 by 91, and then reshape it to be 4 by 10 by 91. So I could do that, or I can just use that. PyTorch doesn't really care. It will do that reshape, unshape operation for us. So we can do logits is self.fc output print logits.shape, and you'll see we get our 4 by 10 by 91. So we have 91 possible predictions for each token for each sequence, right, across our batch. And we can return our logits. And it's as simple as that, right? Nothing crazy happened. That's all it is. That's our forward function. Now the slightly more complicated part is writing our write function, right? So this will be how we generate one token at a time. And so let's kind of get a general picture of how this is going to happen. So the input to our write function is going to be a text, right? Text. Let's say it's hello. And max characters, like how many characters do we want to generate? So we don't really care about that for now. So we're going to take hello. It's going to actually let's pick a shorter word so it's easier. Let's say the text is car, right? So it's going to take car, so it's going to tokenize it, C-A-R, right? We've tokenized it. It's character level, so there we go. Each of these are going to go into a hidden state. Again, I'm just drawing it upside down, but it's the same thing, obviously. Hidden state, H0, H1, H2. This is X0, X1, X2, right? And from car, what we care about really is this last thing right here, X3. I mean, we will also get these outputs here, but what these outputs are don't really matter to us because we already know in car, we already know what, from C, we know the next thing is A, and from A, we know the next thing is R. But from R, what is the next thing is what we don't know. So that is going to be X3 is what we want to predict. And so that'll be our first prediction in the autoregressive task. Once we have X, so there's 2 cases. Case 1 is when we're first starting, we pass in our sequence and we predict the next token, and that's it. So now we can take this X3 and put it here as our next prediction. X3 is what we predicted. Remember, it's autoregressive. And now X3 is going to get passed in here. And obviously there's these connections as well that I forgot to draw. And we want to predict X4. And this is the crucial part. In the very first iteration, we will pass in all of the tokens, but just grab the final hidden state and predict what it should be. And that's it. We'll grab the final hidden state, H2, and predict what it will be. To predict X4, all we need, the only information we need is X3 and H2. So we don't care about H0. Actually, we never really cared about H0 and H1, so we can ignore that. And we don't really care about X0, X1, and X2 either. All we care about is H2 and X3, because H2 encodes the history of everything prior, and X3 is my new input, so H3 will become my new thing to predict X4. And then again, X4 will go up here, X4. X4 will go to make a new hidden state. This will be H4 in this case. And we want to predict X5 now. So in this case, all we care about to predict X5, all we need is H3, which encodes the history, and X4, the new input. We no longer care about X3 anymore. And we just rinse and repeat this operation over and over and over again. So we just need to write a couple little conditions to handle this stuff. There's also a couple, actually we'll get there later, but there's a couple steps about how we actually decode, and we'll talk about that. But for now, let's do def write self text max characters and greedy equals false. And we'll talk about what greedy decoding is in a little bit. Step 1, the text we're going to be passing in. So let's get rid of you now. We don't care about this. We know this is correct. Let's say the text we're passing in is hello. And so we're going to do model.write our text. Let's say we want to generate 10 new characters, unless we don't really care about greedy right now because we're not there yet. So if we print text, and this should be self, we have hello. But obviously we don't want to use words. We need to convert this to numbers. So we need to tokenize our text. So first step is tokenizing the text. And I'm going to call this index, right? Index is going to be torch.tensor. And we're going to do car to index C for C in text. So now we can print out the index. And those are the unique tokens, the numbers that represent H, E, L, L, and O. And that's it. So we can see like 66 is L. So that's our tokenized data. Now this on its own is fine, but we also need to do device equals self.device. Right now we're on the CPU, so it makes no difference. But when we go to the GPU, it might throw an error about like things being on different devices. So we just need to make sure whatever we do is happening on the device wherever this model is set. So there we go. That's our index. We also need to go ahead and generate our initial hidden and self state. So as you notice, right, we basically, the very first step, we pass in all the tokens that we have from our input. So that's fine. But after that, we're just passing in one token at a time. But we need to manually for loop through these tokens because we have some extra logic in here of actually decoding what these things are. So we need to pass in one token at a time. So if we're going to do this one token at a time thing, we need to use all the logic we talked about up here, right? How do we pass in method 2, passing in one token at a time? So we initialize some hidden and self state, and we replace that hidden and self state as we go through one token at a time. Now, one thing to keep in mind, the hidden and self state that I initialized here is num layers by batch size by hidden size, and that's fine. The hidden and self state we will be using will actually just be num layers by hidden size. It's because when we generate the sequence, we're only generating like one sequence, not a batch of sequences. We could also make it like we could generate a batch like at the same time, but that would just make things more complicated. I'm trying to keep this as simple as possible. So our hidden and self state will just be num layers by hidden size. That's what PyTorch expects. If you have no batch dimension, then we just ignore this batch dimension essentially. So we'll do that. So we're going to do hidden is equal to torch.zeros, and it's going to be just like before, self.n layers, the number of layers, by self.hidden size. So we just ignore the batch dimension. And also we need .to self.device to make sure it's on the GPU. And then our self state identically is torch.zeros, self.n layers, self.hidden size, again .to self.device. And there we go. And now it's time to generate one character at a time for the max characters that we have. Now, if you notice here, I'm specifying that I want to generate specifically 10 characters, 20 characters, whatever it may be. In the real world, like when you use a language model like ChatGPT or whatever, they know when to stop. They know when to stop, and we'll see how that happens later. It's typically we have a special token called the end of sentence token. So when the model decides to generate an end of sentence token, then it's done. It stops generating at that point. But we'll see kind of all that later. For now, we're going to do for I in range max characters. Right? We're going to generate this many characters. And this is where we have that little bit of work to do. If I is 0, so we're at the very first iteration. If I is 0, we want to pass in all the tokens, right? CAR in this case. So we're going to pass in all the tokens. So let's make, we're using hello, so that's fine. If I is 0, we're going to pass in all the tokens. So our selected index, right? Things we have selected is going to be our index. It's just going to be everything that's currently in this index. Else, if we're not in our first iteration, so in the first iteration, we pass in all the text, but like we saw later on, all we need is the new token. So we're going to generate x3 here. So let's go ahead and clean this up a little bit. We generate x3 right here. And so all we need to generate x4, a future token, is our new input x3, and we need the previous hidden state h2. And that's all we need. We need x3 and h2 to produce h3, which produces x4, right? Our next prediction. So in this case, if we're not in the first step, then our selected index is just index minus 1. We just need the last index, but we need to add that unsqueeze 0. We need to add that dimension back in, because otherwise it just it would be missing the sequence dimension. We want it to be a 1 token by 1 in this case, rather than just 1. So that's it. So we have everything ready to go. That sets up the indexes. And we can print out selected index in this case and just break. So we can see in the initial one, selected index is all of them. And we'll see what it looks like in the future when we actually get there. But if you look at the shape, dot shape, the selected index is just a vector of length 5, nothing crazy. Yeah, so if we actually index a, if we index, I don't know, let me just mess with it. Without the unsqueeze, if we don't have the unsqueeze here, notice that there is no dimension. It's basically just a number, right? That there's no dimensions here. It's just one number. So we're just adding that number in. So it's a vector of length 1. There we go. So yeah, we have a vector of length 5 here, no batch dimension, and now a vector of length 1 here. No batch dimension, it's just 1. So there we go. Now that we have that, it's time to pass our data through our model. So x is going to be equal to self.embedding. And we're going to do selected index, right? We've selected this index, so we need to first encode it, right? We need to find its embedding from our embedding matrix. Then we're going to do output, and then hidden and cell is equal to self.lstm x hidden and cell. Just like we did before, right? We're just replacing the hidden and cell state with the new hidden and cell state. And this is how we're carrying forward. When I say all I need to predict x4 is h2 and x3, well, h2 is the previous cell state and the previous hidden state, and of course the previous cell state as well. And so that's happening right here. That's my previous hidden and cell state that I'm using. And then x3 is my new token, and that's happening right here, right? Me grabbing the last token that I just generated. And you'll see how we get that onto index in just a bit. So we have our output, and then out is going to be self.fc output, right? Our prediction. So print out.shape. And this is, we have 5 things in this initial sequence that we're passing in, and each one have 91 possibilities, right? 91 possibilities of the output. But we don't care about all of them, right? We don't care about any of these. We just care about for the last token, in this case R, what do we predict for the next token, for x4? So in our case, we have 5 tokens here. All we care about is after O, what do we predict the 6th token should be? So we can index this out. So we can do if the length of out is greater than 1. So in this first situation where we're passing in 5 tokens, this out has a length of 5. In a future case, in the next iteration, where we're just grabbing the last token of our selected index, then this will only have 1, then our output will only be a 1 by 91, and this doesn't really apply anymore, but in this situation it applies, so we just need to index it out. We can do out is equal to out. We want the last token and all the embeddings, and we need to add a unsqueeze 0, so it maintains a 1 by 91 shape. Otherwise, if we didn't have the unsqueeze, it would just be 91. We need to make sure we have that sequence dimension in there. So 1 by 91. So there we go. Now that we've clipped our output, or just truncated our output to the last thing that we care about, now we can compute our probability. So again, just like before, where did I do that MNIST example? In MNIST, right, what we've done, and in our case, but it doesn't really matter, what we've done is produce outputs, 10 outputs, right? So 1, 2, 3, dot, 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 there's 10 outputs. And this is the output for 0, the output for 1, the output for 2, dot, 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 and the output for 9, right? Those are my 10 outputs that it could be. But linear layers can project anything. These numbers can be anything. We want rather the probability of 0, the probability of 1, dot, 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 the probability of 9, right? The likelihood of each of these things, rather than just some unnormalized logit that pops out of them. And so in this situation where we want the probability, well, there's only one way to do this, a softmax, right? That's the way we do it, so that's the way we're going to stick to it. So we're going to do a softmax. We can throw a quick self.softmax in here as nn.softmax, and we can do dim equals -1 because we want to do the softmax along the last dimension, basically the softmax along the 91 possible tokens. So instead of having 91 outputs, I can say the next output, the next token that we predict, what we're having is the probability that it's token character 0, probability it's character 1, probability it's character 2. What is the likelihood? So we can then do probs is going to be self.softmax out, print probs. And what we see here is our probabilities of what is the probability that this is going to be the next token, or this is going to be the next token, or this is going to be the next token, so on and so forth. So nothing too crazy here, right? This should look very familiar because we've seen this before with MNIST and all the other classification examples we've done. It's just a little bit different now because we're predicting possible characters as the next character, but ideally ideologically it's exactly the same thing. So there's nothing too much to worry about. But now the question becomes, how do we pick? So what I have is a probability vector here of telling me what's the likelihood the next token is one of these tokens. And so there's two ways to pick. There's greedy decoding, and then there's random decoding, and then there's other types of decoding methods like beam search or top K or stuff. But we're going to stick to the two common ones today, or easy common ones today. First, greedy decoding. Greedy decoding is just saying for the next token, I'm going to take the most likely token, right? So whichever thing has the highest probability is what I'm going to take. So we're going to do if greedy, right? If it's greedy decoding, then we're going to do our IDX next, right? Our predicted next index is going to be torch.argmax probs. And so we can print IDX next, and let's do greedy equals true for now. And I predicted 29 or 82. Obviously, the model's not trained yet, so it doesn't really matter what we predict. But you get the idea, right? I've picked the index, which is effectively the token, right? The token index that has the highest probability. And this is a fair way of doing it, though gradient decoding doesn't, it depends. Playing with decoding methods is actually important. There's a bunch of ways of, again, doing it. But for now, we're going to keep this simple and just stick to greedy. But we have one other option, and that's a sampled probability. So let's take a look at here real quick. I hope all of y'all have heard of the binomial distribution. So the binomial distribution, if we're flipping a coin, right? Coin flip. And let's pretend it's a fair coin. So you have heads and tails, and each one is 0.5, 0.5. And the binomial distribution, you can sample from a binomial distribution, but a binomial distribution basically says that if I flip 100 times, what is the likelihood I have like 20 tails, or or 30 tails, or whatever it may be? That's the likelihood. But to sample from a binomial distribution is basically a sample from this, right? We have 0.5 and 0.5, so we're equally likely to get one output from it, right? One or the other, right? Or half and half. And so the binomial distribution is intentionally for a binary task, as that's why it's called binomial. On the other hand, if we're rolling dice, right? Rolling dice, right? And to roll a die, there's 1, 2, 3, 4, 5, 6. There's 6 sides, and each one takes a probability of 1/6 if it's a fair dice. To sample from this distribution, we can no longer use binomial because it's not binary, but we can use something known as multinomial, which is just an extension. Multinomial. It's just an extension of the binomial distribution. So we can sample from a multinomial distribution. And the reason we do this, the main reason we do this is to promote diversity of generation. So if we do greedy decoding, for example, it will always take the most likely thing. But maybe we don't always need the most likely thing. Maybe the second most likely is okay, or the third most likely, or something like that, or just something random. And introducing a little bit of randomness to your model typically improves a little bit with our kind of quality of training, or the quality of the generations. Again, there's a lot of types of decoders out there, and I don't want to go into too much detail about them now, but multinomial just introduces a little bit of randomness. So in our case, right, what we have is, let's say our tokenizer is 5 characters: character 0, character 1, character 2, character 3, character 4. And let's say our linear layer predicts the probability of character 0 is 0.1, character 1 is 0.2, character 2 is 0.3, character 3 is, let's say, 0.2. How much do I have left? 5, 6, 7, 8. So character 4 is 0.2. Now, greedy decoding would just say, oh, character 2 is the next one, and that's it. But it looks like we have some other characters here that seem like good alternatives, right? It may not be as high probability, but they may be good, right? They may be fine. So we can randomly sample, and obviously when you randomly sample with like a multinomial distribution, when you randomly sample, you're most likely going to pick the highest probability thing. But sometimes you'll also grab other stuff because it's random. And that typically could help with our generative process. So again, it lets us explore more opportunities or possibilities of generations, and we're not just limited by the argmax operation. So that's all. So we're going to do else idx next is going to be, and what we do is we can use torch.multinomial is already built in, and multinomial expects a probability vector, right? What is the probability of each of the cases? And we just want to grab one sample, right? We only need to grab one sample from it. So there we go. Print idx next, and greedy in this case will be false. And there we go. So we predicted that it should be 41. 41 again may not be the highest probability option, but it is one of the options. And we're hoping as the model becomes more and more confident about the next token, the multinomial probably should pick the most likely thing most of the time. But as there's also some randomness there. So that's basically it. So we have now predicted the next index. Now it's time to go ahead and do torch.cat. We're going to concatenate onto our existing indexes. So index, again, remember, is the existing tensor, the existing indexes of our text that we passed in. Now we're going to go ahead and concatenate onto index our next index next. And one thing to keep in mind, notice how if we print index next dot shape, this is actually going to throw an error because index next dot shape is a 1-by-1 tensor, right? 1-by-1. So it's, one time step, one value. It's just an extra dummy tensor in there. On the other hand, index dot shape has just one dimension, just 5. So we can actually remove one of these dimensions and then concatenate it onto here. So we can do idx next 0. And that will remove one of those ones, index it out, and then we are golden. So now we can take a look at our print index before and print index now. And you can see in this case, we've predicted 11 as our next index that we want, right? It's what we predicted. So using these 5 tokens, we've predicted the 11. And now that we've generated one thing, so this is if I is 0, the first step. Now what we have is, well, we've updated the hidden and self state from this iteration. So this hidden and self state is encoding both the input and basically our history. This hidden self state is now encoding this history of our indexes. And we have this new token. And this is what I was talking about over here. We now have our new token x3, and we also have a hidden self state that encode the history. So all I need to generate my next hidden state and self state is my newly generated token and the previous hidden and self state. And so my hidden and self state, here is the previous hidden and self state already updated and ready to go for the next iteration. And I have generated this new token 11 here, which means in this next iteration, when I is not 0, we can just go ahead and grab that last token, that token that we went ahead and generated. Now that we have this, we've generated an index. This whole thing will just kind of autoregressively keep going. And then the last step is, well, let's take a look, print index. These are all of our generated indexes. So we're good to go there. But it's time to actually take our indexes and return them back to text. And that's all. So we can do gen string is equal to, and now we go the other way. We're going to do idx to car, idx to car c. So we're going from index to character now. We're going backwards. For c in index. There we go. And just to, I think I threw a sanity check in here. Obviously, these things have to be integers, so I just make sure it's casted to an integer before we go to index. So now we can do print gen string, and there's our predictions, right? These, obviously it's garbage now because we haven't even trained the model yet, but these are our predictions. But we need to just take this and put it all back together. So we can do gen string is equal to space, or actually no space, because space is one of our characters. So we're just going to stick it together. Dot join gen string print gen string, and there we go. So we predicted hello and then a bunch of garbage characters because obviously this model has not been trained yet. If we change this to be 100, well, there you go. We've generated 100 new tokens, so on and so forth. I think that's it for our model, right? So now we can return our generated string. Good. So again, the main idea here is we pass in some text, we tokenize them, we then go ahead and create our hidden and self state, loop through how many characters we want to generate, pass it to our model, generate one token at a time. And because we're generating one token at a time, we actually need to implement this for loop and use this method rather than just passing a sequence to our model. Generate one token at a time, and then produce our output. We could actually, the other option, right? The other option is we could have done it this way, but this is actually less efficient. Like if we have cell 1s, character 2, character 3, character 4, what we could have done actually is pass all 4 characters to our model at once using the PyTorch, like, pass the whole sequence in, and then index the hidden state and predicts 5. And then we could have just went ahead and passed all of this in again and produced C6. And then we could have passed all of this in again and then produced C7. The problem with this is that we will repeat this for loop over and over. Like, we're going to have to for loop from C1 through C4 to produce C5. But then we're going to have to, again, for loop through C1 through C5 to produce C6. But that for loop from C1 through C4 is the same no matter which iteration you're doing it on. So it's just repeating work. Like, it's just less efficient because we're repeating work that we don't really need to do again. So that's why we spent a little bit extra effort in trying to do this well. Now let's go ahead and train this model, right? So there's going to be one last complication, and you'll see that in just a bit of how we actually train the model, but it should be pretty easy. So let's define epochs as 3000, max len is 300, evaluate interval, so how often do we want to evaluate our model? Let's also do 300. The embedding dim, so embedding dimension, let's do 128. The hidden size is, again, 256. Our n layers, let's do 3. The learning rate, let's do 0.003, doesn't really matter right now, and then batch size is 128. So device is going to be CUDA if torch.CUDA.is available, else CPU, but I have CUDA, so that's fine. And then we're going to do model is equal to LSTM for generation. And this is going to be embedding dim. The number of characters is len car to index. Our hidden size is our hidden size. Then we have n layers, and then device. So there's our model. Nothing too crazy, right? So you have our model right there. We also need an optimizer. Let's just use optim.atomw model.parameters. Learning rate is learning rate. So there we go. Nothing crazy. And again, we have our loss function, which we said this is again just a classification problem, right? So if it's classification, then we're using CrossEntropy. So CrossEntropy loss. We have our data set, which we created. It's the data builder, just like that. And now it's time to train our model. So we're going to do for epoch and range epochs. Actually, it's not technically epochs. In this case, it's iterations. So this will be 3000 iterations, and each iteration has a batch size of 128. So let's be more correct. So iterations, right? Because we're not actually looping through all the data, so it's not technically an epoch. So we can do for iteration in iterations. There we go. We first need to grab a batch of data. So we can do input texts labels is equal to dataset dot grab random batch with some batch size that we provided, batch size. That produces some data. We also need to make sure input text and labels are both on the GPU. So input text dot to device, and then labels dot to device. There we go. And we can go and do optimizer just to zero out the gradients before we go to compute anything. And we can now do output is equal to model input texts. And let's break. Let's print the output dot shape. Let's see what went wrong. So it looks like expected on the GPU, so this always happens. Did I not do the conversion? Oh, yes. Our model also needs to be on the device, right? So there we go. And we now have our output. So we have a batch size of 128. We have 299 outputs. And again, let's refer back to our picture, right? We had 6 things in our sequence here with a batch size of 1. So we had 5 inputs, the capital of France is, and then the outputs are just going to be offset by 1. Capital of France is Paris, right? So that is our autoregressive task, right? We just offset them by 1. So we have 300 things in our sequence. So we have 299 299 inputs, and offset by 1, 299 outputs. So there's our output.shape. And the important part is we want the model to get, when I pass in the capital of friends is, we want it to predict all of this correctly at the same time. And so this is a good opportunity for me to just batch it up. But we have a little bit of a problem. Output.shape, print label.shape, or labels.shape. So our output is 128 by 299 by 91, and our labels is just 128 by 299. So our model is predicting 91 possibilities at each of these time steps for each of the samples in our batch. Here are the correct answers. So for us to do cross-entropy loss here, again, this is just how PyTorch works. We need to go ahead and just clean up the way we set this up. So there's a couple ways we can do this. The easiest one is if we do, let's see, output is equal to output.transpose 1, 2. So print output.shape, print labels.shape. So if you see here, we have 128 by 91 by 299, and then 128 by 299. So actually, let's just look at the cross-entropy loss PyTorch, right? They're expected shapes. So they expect a n by c by any dimensions we have. So n by c by d1, d2, dk. On the other hand, the target can be n by, without, so c is the number of classes, n by d1, d2, dk. So in our case, we have n, number of samples, by c, 91, it's 91 possibilities, by some, other dimensions, whatever it may be. So that's our d1, d2. We only have a d1. So we have n by c by d1. So n by c, number of choices, by our first dimension, d1. Our labels, our targets, must be n by d1, right? We don't have a d2 or anything like that. So we have n by d1, 128 by 299. So this is one way of working with the PyTorch cross-entropy. The other one is we can just go ahead and flatten. We can do output is equal to output.flatten. I think 2, print output. Actually, that might not work. So we can actually do, let's do it this way. Let's do batch size by sequence len by embed dim is equal to output dot shape. So we can print out batch print output dot shape just to verify. So it's batch size by sequence length by embedding dim. So the other option we can do is we can do output equals output dot reshape batch size times sequence length by embed dim. And then targets is going to be not targets, but labels is going to be labels dot reshape batch size times sequence length. So now if we print output dot shape and print labels dot shape, we get something like this. So we have 38,272 tokens in this batch, each with 91 possible outputs. And here are the 38,272 correct answers of what those outputs should be. And so hopefully this makes sense, right? So doing it this way is fair game, and doing it this way is fair game. Both are equivalent. It's just how PyTorch expects it, right? So we're just going to give it to them how they want it. So now we can compute our loss, so the loss function, which we did as cross-entropy again, because this is a classification task. This is a loss function between the output and the labels. And we can print our loss to see what it looks like. Looks like we have a small mistake here. Output, not outs. There we go. So we have a loss of 4.5072. Fine. Now it's time for us to update the model and do everything like we've done before. So loss.backward, optimizer.step. You can throw other stuff in there like like gradient clipping and more fancy stuff, but we talked about it, and I'm trying to keep this simple, so we're going to do it this way. And we're going to do if iteration percent evaluate interval. So iteration evaluate interval. So every 300 iterations, we want to evaluate the model, and the best way to evaluate the model is just by trying to print something out, like getting the model to generate something. So we can do is if this is 0, we can then do print. Let's just throw a couple of breaks in here. And we can do print epoch, epoch. So we've printed out which epoch are we on? Print loss, loss.item. There we go. So we're printing out what's the current epoch. Or I guess this isn't epoch anymore, actually. This should be iteration. There we go. We print out our loss. And now it's time to generate some text, right? So we can do, oh, whoops. Don't want you to train just yet. Stop. Okay. Generated text is going to be model.write. And we have to give it some starting point. So I mean, it's Harry Potter, so we can do spells, right? So whatever. And max characters equals 200. So we are going to give it some starting text to start generating from. And we're telling it how many characters we would like to generate. So there we go. And then we can print sample generation. And then, again, don't want to run it. We need to then do print generate text, right? Or generated text. And then we can just throw another one of these underneath so it separates out. And that should be good. So let's see how this works out. So yeah, so as you can see, initially when we start training, this is basically garbage, right? This doesn't look like text at all. But as it's training, you can see it's starting to look more like text. Like we're starting to see words. Now we're starting to really get words, right? Spells, thinker, professor, mather, right? Moment, spiraled, spells, how they like the moment, so on and so forth. So this, and now we're starting to get some characters. Harry, Hermione had content, shiny bangs. Spells, they murdered in dinner. You know, it's basically garbage. And this is the look. We also got Muggle. We got Dumbledore, Malfoy's. So it's learning, right? It's doing stuff, and you know, whatever it may be. This is just kind of a proof of concept of how we sell. But this sets a lot of this up. So there's another great video. So a lot of this was inspired by Karpathy's GPT video, so I would definitely recommend going and watching that. He just uses a transformer rather than an LSTM here. But this sets the stage for a couple different things. First of all, this is a sequence model that can generate. And so now that we know that we can generate with the sequence model, you can plug in any sequence model you want. It doesn't really matter what type of sequence model you're working with. It could be a LSTM, it could be a GRU, it could be a transformer, it can be Mamba, it doesn't matter. It can be any sequence model for this generative task, which is great. The other thing you notice is character level is garbage. Like we see spells, things, Yeasley, though I'm sure you, son, we also. So it's looking like English. Like we're getting something that looks like English, but it really isn't. And that's because the character level is just too granular, and the model can't really learn anything valuable at the character level, because the embeddings we're learning don't really represent the meaning of anything. Characters don't mean anything for the most part, right? So this is why word level, or definitely subword level, like tick token, BPE tokenizers, things like that, is the way to go. So this is, again, a high-level overview. What I wanted you to get out of this is how we can use the LSTM or any recurrent neural network for the many-to-many task. Because last time we just looked at the many-to-one mechanism. Now that we have this, there's only one thing left for us to do in this kind of initial sequence of tutorials, and that's we've learned how to train models. We've learned convolutions, we've learned regular linear layers, we've learned these recurrent neural networks, we've learned how to build a data set, we've learned residual connections. So we've seen a lot in all this content. What we haven't done yet is actually try to train a big model on lots of compute. And so the next portion may be more inaccessible to a lot of y'all, but please do try to follow along because it is important, especially if you're working on a desktop with multiple GPUs, or if you're working in a HPC environment, like a lot of universities will have campus clusters and things like that that you can utilize. Well, if I gave you 2 GPUs, how would you train on 2 GPUs? And there's actually more stuff that goes into it. We need to log our data. We need to log the results. We need to checkpoint the model. We need to be able to restart. We need to be able to distribute the computing and that sort of stuff. So the whole next video, we'll be taking the ResNet 50 model that we looked at a few videos ago and actually reproduce its results on ImageNet. And so we'll be copying the PyTorch training recipe for ResNet and implement it using the Hugging Face Accelerate platform, which I personally use for all of my research now, which is great. So either way, let me know if you have any questions, drop it down in the comments below, but I will see you in the next one.